Welcome to Sigma Solver guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to look at a topic from cryptography and network security. So let's read the question first. Using the Euclidean algorithm, compute the greatest common divisor and the parameters st of 1819 and 3587, right? So some of the prerequisites that someone should know before tackling this sort of problem is what we will discuss first. First is greatest common divisor. So for just a quick refresher, for two integers a and b, GCD AB is the largest integer that divides both these integers. Okay. Next concept is division with remainder. So for integers a comma b which are greater than 0, there will exist unique pairs of q and r such that a equals bq plus r, right, where r will subject to this condition where 0 is less than equal to r and r is less than b, right, while we will also know that q is known as quotient and r is remainder. Next we come to the Euclidean algorithm itself. So the algorithm states to repeatedly divide and keep the remainders in the calculation. So for GCD calculation, we can have GCD of a comma b equal to GCD of b comma r1, GCD of r1 comma r2 and so on. Now how these r1s r2 are derived and used, we will see in the solution below. So we will do all these steps until we get the remainder equal to 0, right, and we will know that the last non-zero remainder in this process is going to be the GCD of a and b. Next we come to the extended Euclidean algorithm. So it not only finds the GCD of a and b, which does the actual one, but it will also find integers s and t such that GCD of a comma b is equal to SA plus TB, right. Now the solution that we'll have for this particular problem will be something like this. We'll start with the largest number first, which is 3587, which is equal to 1 times 1819 plus 1768. Simple calculation. In step 2, we'll take the number from here, right, and then try to find these numbers, the q and r, right. Similarly, in the next step we'll do the same and continue to find the quotients and remainders in this order. In the fifth step, when we land, we see that we got the remainder 0, right. Here the quotient for 17 is 2, but remember the quotient here is actually the remainder in the last step, right. So as per the rule, the last non-zero remainder from above is 17, hence GCD of 1819 and 3587 will be 17. Now let's try to find S and T. So in order to find S and T, we will use extended Euclidean algorithm. We now want to express 17 as a linear combination of 1819 and 3857. In order to do that, we will use something called as coefficient table. We will track each remainder, let's say Rk, as Rk equals xk times 3587 plus yk times 1819. This is how you linearly represent the equation. Now we will start with the initial phrase, which is k, Rk, xk and yk stated as columns, and the initial step or 0th step will take the largest number and thereafter the smaller number, right. We will take xk as 1 and yk as 0. Remember, this particular equation as we have it right here will suffice the above equality always, right. K just denotes the marker of the counting. Then we come to first step. Likewise, it does also fit into the equality. Next we come to the new rows that will be formed from this calculation onwards. So Rk plus 1 will be R of k minus 1 minus Qk times Rk, whereas xk plus 1 equals xk minus 1 minus of Qk xk. Similarly, for yk plus 1 equal yk minus 1 minus of Qk yk. Now all these follow the similar pattern, so it will be easier to remember. Now in this case we will know Qk is actually the quotient in the division step, right. So from the first step, as we saw above, we can take 3857 equals 1 times 1819 plus 1768. In this case, Q or quotient is 1. Hence, R2 will be 1768, X2 is this, which is 1, Y2 is again minus 1, right. Similarly, just put in the values and you will let know what is going to be the value next. So we put all these information. Now you see the counter increased to 2, Rk is 1768, Xk is 1 and Yk is minus 1. Now we put the same thing again into the equation, which is 1819, 1 times 1768 plus 51, right. We take Rk from here and the actual number is from line 2, which is k equal 1, right. So we will take that and then try to find which q will fit the equation. So it is 1. Now we can again find R3, X3 and Y3, right. We get these values, we will have to put them in the next row, right. Then we will get 51 as the new Rk, we will again have to put that into the equation, right. And as you can see 1768 is just the previous Rk, that is Rk minus 1, and here we see that we got 34 as the coefficient, right. We will put those numbers into account. We know that the next quotient is going to be R4, so we put that here and likewise calculate X4 and Y4. We put them into the table again, and this time in step 4 we will see that we actually get 17 into the remainder, right, which is what we want. So we get this time the quotient as 1 again, hence we calculate R5, X5 and Y5 using the above formulas. Then we will see that once we put them into the equation, we get row 5 as such, where Rk is 17, Xk is minus 36 and Yk is 71. Now these are the two numbers that we would need to find S and T, which is 17 equals minus 36 times the first number, right, Xk, and Yk times the second number, right. So if we reorder them to match the problem statement, the parameters of X and T of 18, 19 and 3587, this would be 17 equals 71 times 1819 minus 36 times 3587. So therefore GCD of 18, 19 and 3587 is 17 and S and T are 71 and minus 36 respectively. We can also verify that using this equation. Now from this above method of solving, we can get to the inference that Euclidean algorithm works with remainders and not just numbers to get to the GCD fast. Another important deduction is the pair S comma T 71 comma minus 36 is not unique, right. We see that if D equals GCD of A comma B and that is equal to 17 and the ratio A is to B is fixed, right, then any number such that S dash equals S plus K times 3587 upon 17 comma T dash equals T minus K times 1819 over 17 will yield the similar result, meaning that these S dash and T dash can as well be plugged into the same equation. So for this same integer K, S dash and T dash will also work, right. Now we will look at some of the modifications that can be made. Just to highlight the important ones, one of the modifications is pure black substitution method, which is to repeatedly substitute earlier equations into later ones. That would be good for smaller numbers, but when it gets messy if we have larger numbers. Then there is binary GCD, also known as Stein's method. It uses only subtraction and division by 2 shifts. It is often faster on computers. Then there is modular inverses, like when you use AX equal to 1 mod M and you want to find X. So how we use Euclidean formula into that is something that we do here. Then there is solving linear Diophantine equations, right, where something like AX plus BY equals C and we need to check whether C is kind of a multiple of GCD of A and B and likewise, right. So all these are basically discussed inside the Sigma Solver community, including more questions on this same topic for your practice. So if you do want to join the community, you can simply do so by clicking the link in the description below. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.